Hi class. In case you're still struggling with ramps and how to do this calculator lab, I'm going to go ahead and make up some fake data here and show you how to solve for the coefficient of static friction between your calculator and the ramp. First thing you're going to do is place your calculator on the scale. I'm just going to make up a number here. So let's just pretend that your calculator has a mass of 0.5 kilograms. Fg is going to be your mass, 0.5 times 9.8, which is 4.9 newtons. And then you're going to put your calculator on top of your ramp. You're going to slowly raise up that ramp until you just see it move. So let's say I see it moving at about, 50 degrees. I'm actually going to go ahead and use 49 degrees here because we want the coefficient of static friction. So that's right when it was not moving. And we want to get the highest, we want the maximum static friction here. So let's say we do that, it's 49 degrees. We lower the ramp, and then we raise it back up again, and maybe we get, 50 degrees. And then we do the same thing again, and maybe we get 51 degrees. So we've done our 3 trials, and the average angle right there is 51 degrees. Just like any other problem that we've done, we want to draw a force diagram. So gravity pulls straight down. Our normal force, you know what, I'm going to angle that a little bit more to make sure it's perpendicular to the track. And then we have, that is friction force right there. Just like every other problem, there's going to be an angle involved here in this chapter. So this right here is my angle theta. So I'm going to make my triangle, which we've already learned in class. I'm going to go ahead and actually move FG over here. So there's FG right there. I've got my angle theta in the right place, which means this right here is FG sine theta. And this right there is FG cosine theta. So once we've got our angle, we've got our mass, we've got our FG, and we've got our force diagram, we can go ahead and start solving for the coefficient of static friction. We're going to solve for Fn here using our vertical forces. So remember, vertical forces are in this plane right here. So when I go ahead and I write out F net equals m times a, our acceleration, by the way, because we're doing coefficient of static friction here, the acceleration everywhere is 0, vertically and horizontally. So my acceleration is 0. I'm going to go ahead and say that the positive direction is going to be in the direction of Fn. So I will say Fn is positive, and therefore I'm going to subtract off the opposite direction, which will be Fg cosine theta. And because acceleration is 0, I can make this 0. If I rewrite that, that means Fn is going to equal Fg cosine theta. And Fg cosine theta is going to be 4.9, that's Fg from above, and then the cosine of 50 degrees. So at this point, you go to your calculator, 4.9 cosine 50, and I get 3.15 newtons. So that's the force of the track pushing up on the calculator. Then I'm going to get to the next part. So solve for FF using your horizontal forces. So again, I'll start off with F net equals m times a. We go back up to our force diagram, and our 2 horizontal forces are FF and Fg sine theta. I'm going to go ahead and assign the direction down the track to be positive. So what that means is Fg sine theta, which points down the track, is going to be my positive direction, and friction tries to push the opposite way. It's trying to prevent movement. So FF equals m times a. Now remember that the acceleration is 0 because we're doing coefficient of static friction. So that's why I kind of rounded down my angle, and I used 49 degrees when maybe my protractor said that the track had allowed the calculator to start moving at 50. So I kind of round down maybe a half degree or degree because we want the coefficient of static friction And right before the calculator started moving, the acceleration was 0. So just like before, FG sine theta is going to equal FF. So FG is 4.9. The sine of, I believe we were using 50 degrees, right? Yep, 50 degrees equals FF. And then you would go to your calculator. FF is going to equal 4.9 sine of 50. So that's 3.75 newtons. So it's a real quick, easy last step. Coefficient of friction is FF equals mu times Fn, and this is going to be static because it's not moving. So we got our friction force, I should say, 3.75 newtons. We're trying to solve for mu, and our Fn was 3.15. So mu is going to equal 3.75 divided by 3.15, 1.19. So remember, this is a unit right here, or I should say this is a symbol that means like how smooth are the surfaces. Usually ranges between 0 and 2. Now I made this number up. 1.19 is pretty high. In fact, I would actually expect 1.19 to be with rubber feet. I bet you with no rubber feet on your calculator, just your calculator on a smooth track, it might be 0.1, 0.2, or 0.3, depending on your calculator. And when you have rubber feet on, you're probably going to get maybe 1, 1.5, 0.8, 0.9. So I actually just made these numbers up, and it actually came out higher than I would have expected. So just be aware of that. And then the second part, when you do the lab, you will use rubber feet. So you should notice that what you get in part 2 should be a higher coefficient of static friction than part 1. If you don't have a calculator with rubber feet, feel free to choose a different surface, water bottle, pencil, something that can rest on the track. Just kind of make a note on the top of your lab for me that you use something besides the calculator with the rubber feet. I hope that helps out, and thank you very much.